Good evening, everyone. Welcome to the ICTS String seminar. So today we have Luca Iliesiu from Stanford, who will be talking to us about on the quantum mechanics of near extremal black holes. So over to you, Luca.
Thank you very much for the invitation. Please feel free to ask as many questions as possible. I just wanted to give kind of an overview talk about all the work that I've done regarding corrections to the quantum corrections to the black hole entropy in the case of extremal black holes. So please ask as many questions as possible. So this is work that I've done mainly with Joaquin Turiachi and Samir Murthy, but also reference a number of past works that involved these co-authors as well. So a major problem that we've made a lot of progress in the past years in answering is to what degree the gravitational path integral for a variety of black hole observables really reproduces features of conventional quantum mechanical systems. So we believe, due to holography, that black holes should be dual to a conventional quantum system, but at this point, that's a conjecture, especially for black holes in flat space. So we'd like to understand to what degree that's true. So in this talk, I'll try to answer three related questions for the special case of extremal and near extremal black holes that will help us understand this correspondence a little bit better, hopefully. So a first question that one might want to ask about any quantum system, it's probably one of the first questions we learned to ask in our first quantum mechanics course, is what is the energy gap between the ground state and first excited state in the quantum mechanical system? In the language of black holes, the same question is what is the energy gap between extremal black hole states and the lightest near extremal black hole states? And there have been various expectations for what this gap is that have changed over the years. But let me preface my talk by introducing an expectation that came from string theory in the 90s, from resolving a problem posed by Preskill and collaborators. The problem posed by Preskill and collaborators was that extremal black holes or near extremal black holes always have an energy scale at which there is a breakdown of black hole thermodynamics. What that concretely means is that as you lower the temperature of a near extremal black hole, eventually you reach a point where the energy that it has above extremality is not enough to radiate even a single unit of Hawking radiation. And the energy at which this happens is typically referred to as the gap scale. It's referred to as the gap scale because in string theory examples of Maldacena, Susskind, and Strominger, this was really identified as an energy scale above extremality, as the gap energy scale above extremality, at which there are no black hole microstates. And to be very concrete, this energy scale for Reinstein-Nordström black holes in 4 dimensions scales in this way with the charge of the black hole. So essentially, you could view this energy scale as a polynomial in the entropy of the black hole. The entropy of an extremal Reinstein-Nordström black hole scales like Q squared. So E gap scales like 1 over the entropy to the 3 halves. So this is a very tiny energy scale, and yet still it is not necessarily exponential in the entropy of the black hole, as one might expect for a variety of quantum systems. So my first goal is to answer whether this gap scale is truly present for a black hole, for a variety of black holes, both the simplest black holes, such as Reinstein-Nordström black holes in electromagnetism, and more complicated examples, such as black holes in supergravity. A related question is that if there truly is a gap scale, Then if there truly is a gap, then the semi-classical calculations of black hole entropy would suggest that extremal black hole states are truly degenerate. Specifically, you all probably know that the entropy of a black hole is given at the semi-classical level by the area of the black hole. And since extremal black holes don't have any temperature in a sector of fixed charge, this means that the degeneracy of the black hole would be given by an exponential of the area. But for instance, for the simplest examples of extremal black holes that we have in mind, such as Reiser-Nordstrom black holes and electromagnetism, one might wonder what protects this degeneracy if it's really there. Usually, if we see degeneracy in a conventional quantum system, we find some symmetry or topological principle that protects that degeneracy. But in the case of Reiser-Nordstrom black holes, we have no idea whether such a principle actually exists or such a symmetry actually exists. So we should either explain why the degeneracy is there, or perhaps why it's actually absent. And if we find a degeneracy, or in the cases in which we find a degeneracy, we should really find that this degeneracy is an integer. This is one of the hallmarks of any quantum systems, namely that the degeneracy, that there is a genuine state count in the Hilbert space associated to the theory. So we would expect that all degeneracies are integers. And the final question that I like to ask, I'm not sure whether I'll have time to answer it today, but perhaps for those that want to stay a bit longer, I can talk a bit more about it, is can the gravitational path integral reproduce a microstate count, including the integerness of such a count? So before I start answering these three questions, I want to tell you what the gravitational path integral seemingly tells us for extremal black holes. So at leading order, the gravitational path integral is just given by a saddle point answer. So the partition function of a black hole is given by the exponential of minus the gravitational action evaluated on the black hole solution that we're interested in. So suppose I take extremal Reiser-Nordstrom solution and plug it into the action. What do you get? Well, as I alluded to earlier, at leading order, you get an exponential in the area of the black hole. However, people have computed over the past couple of decades what happens at subleading order as well. Namely, if you take the action and instead of just plugging the saddle point, you expand the action to quadratic order around that saddle point and perform the Gaussian integral over all the fields and the metric in your theory. The answer that you get is that this semi-classical answer that's given by area over 4G Newton receives logarithmic corrections, where the exact coefficient C of the logarithm that I will talk about more concretely in a little bit of time, the exact coefficient depends exactly on the matter content, massless matter content of the theory in question. But the important structure in this result is that, or the important feature of this result is that if I make a black hole with a very large charge, that means that its area could be arbitrarily large. This degeneracy still seemingly remains extremely large, regardless of what the matter content of the theory is. This doesn't tell us why Reiser-Nordstrom black holes and electromagnetism would have a huge degeneracy. In fact, it would say that quantum correction suggests that degeneracy is still present. So to answer question 1 and question 2, for both non-supersymmetric and supersymmetric extremal black holes, I want to quickly revisit the computation of the logarithmic corrections that computed this log S0 piece that was done by Ashok Sen and collaborators. So let's start with the simplest black holes that we know, non-supersymmetric Reister-Nordstrom black holes in 3+1 dimensions. So as you go close to extremality, the black hole solution in its near horizon regions takes a very simple form. The space-time separates into two parts, an ADS2 part and the spherical part. The ADS2 part combines the radial space direction with the time direction, and the S2 are just spheres that very slowly, as we move in the radial directions. As I said before, what one has to do in order to compute the partition function of such black holes is take the solution or this background and plug it into the action and then compute things to quadratic order. So what happens at quadratic order? Well, there are two types of modes that we have to include when we expand all the fields, including the metric up to quadratic order for perturbations at mu, gauge fields, and all other fields. First, there are modes with non-zero eigenvalue in the quadratic expansion of the action. So this is at exactly zero temperature, at extremality. When I encounter such modes, it turns out that Sen and collaborators found a very elegant way of treating them by using a heap kernel computation, and the result that one obtains from this computation is non-ambiguous. You obtain that the one loop contribution of all these modes is given by S naught, again, to some power that depends on the matter content of the theory. However, in addition to that, there are zero modes of the action, namely modes that don't carry any weight in the quadratic expansion. Whenever we encounter zero modes, what we should do is, at least scalar zero modes, what we should do is perform the path integral fully over those modes, not only to quadratic order. The zero modes in this case, very explicitly, turn out to be large diffeomorphisms of the metric and large gauge transformations of the U1 gauge field under which the black hole is charged. So we want to perform this path integral exactly. Curiously, a feature that's actually quite important in what I'm about to say is that these zero modes are not only zero modes at quadratic order, they turn out to be zero modes at all orders in perturbation theory in the action of these extremal black holes. So to be concrete, these large diffeomorphisms, I want to tell you what these large diffeomorphisms are. These large diffeomorphisms are modes that keep the scalar curvature, the local scalar curvature of the space-time the same, but however have a non-trivial effect on the boundary of space-time. So in this case, in the near horizon region, what this means is that it has a non-trivial effect on the way the near horizon region is glued to the asymptotically flat region. To evaluate the one loop determinant of these for these solutions, we just have to multiply the answer from the non-zero modes by the answer from the zero modes. And if I'm just interested in if I'm just interested in the S naught dependence, what Sen and collaborators did was that they managed to extract the S naught dependence in the path integral measure over the zero modes of the metric and the zero modes of the gauge field that I didn't write explicitly here. But in total, what one finds is S naught to this power, where NS, NV, and NF are the number of massless scalars, vector, and fermionic fields that are coupled to my gravitational theory. And this factor of 964 over 180 comes from the contribution of the metric degrees of freedom. But What you're left over is an integral over. You still have an integral left over the zero modes that are now rescaled to be such that the integral is seemingly independent of S naught. And this integral is given by an integral over all large diffeomorphisms of the space-time, divided by the space of isometries. So in this case, the space of isometries of the space-time turn out to be in the near horizon region. There's an SL2R isometry, which corresponds to the isometry of the ADS2 part of the space-time. And there's an SU2 isometry, which corresponds to rotations on the internal sphere. And the large diffeomorphisms parametrize how the shape of the boundary in the near horizon region changes, as well as it also parametrizes how fluctuations on the sphere as I go around the boundary of ADS2. So these large diffeomorphisms turn out to be parametrized by a product of two spaces. One is dFS1. These are just diffeomorphisms of the boundary circle. So this is what's quotiented by SL2R. And the other one turns out to be loop SU2. This is the space of functions mapping from the group SU2, the space of function mapping from the circle to the group SU2 manifold. And this is quotiented by SU2. So we still have this integral left to do if we want to truly understand the one loop determinant in this theory.
Yes? I have a question.
Yes.
Is it SU2 or SO3?
Oh, good. So it depends whether, it depends whether we allow for fermionic black holes or only bosonic black holes. So the answer is it depends whether in order to, how should I say this? What distinguishes things is whether or not if I go around the black hole once, if I do a 360 degrees rotation, all fields come back to themselves or not, or minus themselves in the case of fermionic fields. So this differentiates whether I need to integrate over loop SU2 over SU2 or loop SO3 over SO3.
Thank you.
Okay, so in order to really find the one loop determinant, we in principle have to ask what the integral over these zero modes is regularized to. Perhaps it's regularized to 0, to a finite number, or to infinity. Of course, it's very important to answer this question, because if the answer is regularized to 0, then the meaning of the one loop determinant in the case of these non-supersymmetric Reinstein-Nordstrom black holes will be completely different than if it gets regularized to a finite number. And the way to ask this question unambiguously and in a scheme-independent and a regularization scheme-independent way is to ask what is the ratio between the extremal black hole partition function and the black hole partition function once I turn on a temperature. And it turns out that if I turn on even a small temperature, these modes get regularized. Specifically, if instead of expanding around the purely extremal background, I change my background a slight amount in order to go not at extremality, but have a black hole near extremality, one can redo the entire previous computation. The modes that were previously non-zero modes get affected only very little. They already had non-zero weight, so turning on a perturbation in T doesn't do much. But the modes that were previously zero modes turn out to now get a non-zero weight. To now get a non-zero weight that is roughly proportional to the temperature itself. So essentially, the things that were zero modes at zero temperature now become modes that have very large fluctuations because they have very small masses at finite temperature. For Reinstein-Nordstrom black holes at fixed charge and angular momentum, it turns out that the integral over the non-zero modes remains unchanged. So it gives this factor at leading order in the temperature, but the integral over the previous zero modes, the now near zero modes, turns out to give exactly this quantum mechanical system on the nose at quadratic order, and one can show that this persists actually to all orders in perturbation theory. So here, epsilon parameterizes the large diffeomorphisms associated to Dfs1. The effective action that we observe appearing at quadratic order in this case is what's called the Schwarzian action. So it's a higher derivative quantum mechanical theory, which is a higher derivative quantum mechanical theory that you could interpret as living at the boundary of the ABS2 region. This appears, this mode epsilon also couples to all the other modes. However, it couples in a way that is suppressed by orders of 1 over the entropy. The important thing to observe in this quantum mechanical system is that the scale that I mentioned at the beginning, which was the gap scale, actually appears as the coupling of this quantum mechanical system. Namely, this factor of 1 over q cubed, if you remember, was exactly proportional to 1 over E gap. And it turns out that in this the quantum mechanical system, one can do a rescaling of time, of the time u, such that the limits of the integrand here become independent of the temperature. And in that way, one actually sees that the partition function of this quantum mechanical system does not depend on the temperature and this energy scale E gap independently. Instead, it only depends on the ratio between the temperature and the gap scale. So namely, after this rescaling, time such that time goes from 0 to 2 pi, let's say, what one gets is a rescaling of the overall action by a factor of the temperature. So this is actually the new effective coupling of the theory. One thing that I kind of swept under the rug, but I should mention, is that in the calculation that I've presented here, we have actually already integrated out modes that live in loop SU2 over SU2 and loop U1 over U1. Sorry, this should be U1. These were the large diffeomorphisms of the sphere and large gauge transformations of the U1 gauge field. And it turns out that they don't actually have any non-trivial effect once we fix the angular momentum and U1 gauge charge of the gauge field. This is because roughly because the integration space for these zero modes turns out to be compact, and when one studies these modes in a sector of fixed angular momentum and fixed U1 charge, it turns out not to give any additional one-loop corrections to the partition function of these black holes. Nevertheless, the presence of this loop SU2 over SU2, the presence of this large diffeomorphism on the sphere, will actually turn out to play a very important role in the supersymmetric case, and that we will discuss shortly. But
I have a
in any
question.
case, yes.
So this H or the A that you're expanding in, they are not gauge invariant objects. I mean, so you must be doing some sort of gauge fixing, right?
Sorry, who?
The H mu nu is not a gauge invariant
Yes.
object. It's
Yes, but I'm
So-
integrating H mu nu out.
yeah, true. But I mean, you have to gauge fix in some way, and that entails bringing in ghosts and fuzzy Popov determinants and all that. So how
Yes, yes.
why aren't the ghosts mattering here? Shouldn't there be a contribution from the ghosts as well?
Yeah, in some sense, well, let's see. In some sense, the presence of the ghost is perhaps swept under the rug in the measure of these largely fiomorphisms. It's for all the other modes. So for the non-zero modes, one took care of the ghosts using the techniques that Ashok and collaborators developed.
I mean, you've already gone from ADS2 to S1. That got rid of all the gauge modes essentially.
No, so when you go to no, you didn't go from ADS2 to S1. You just integrated all the modes out except for these zero modes.
Yeah, well, the H from
Are you asking
H
about
menu,
what are you asking about what ghosts are associated
I'm
with
just
zero
trying to
modes?
interpret the question, which is that the H menu is a field over ADS2, and you use JT gravity, and then you fix all the stuff in JT gravity, and you come to the boundary, which is, and all of that got rid of the ghosts of gravity, basically.
Right. Yeah, perhaps the only thing I would say is that I think perhaps there is a way of interpreting this integral over d epsilon to write the measure of this path integral as a path integral over fermionic fields associated to the ghosts that these zero modes would have.
I think that's to get rid of the SL2R isometries. That's what gets rid of the SL2R. But I think the question was about 2D gravity more than the boundary itself.
Yes. Okay, yeah. Thanks a lot for the comment, Subir.
I think the ghosts don't have any normalizable zero modes anyway. Right, so they have all. I mean, whatever ghosts we had have already gone in the non-zero modes.
Right. Yes, I think I agree.
Normalizable modes that you are integrating over.
Right. Okay, maybe let's go ahead, and if there's another question about the ghosts, I'll answer it in a second. Okay, so the new feature that we see now is that as we tune the temperature towards extremality, as we tune the black hole towards extremality and make this temperature smaller, this path integral can actually not be evaluated through a saddle point approximation. Instead, it's a strongly coupled theory. That's because the coefficient in front of the Lagrangian can be arbitrarily small. So that's what it means to be a strongly coupled theory of the things that were zero modes at exactly zero temperature. But now we found that they're not zero modes, so we'll call them would-be zero modes. And the fact that this theory is strongly coupled as we approach extremality is precisely what signals the failure of the semi-classical calculation that Preskill and collaborators found in the 90s. So essentially, the breakdown of thermodynamics that they observed could be simply rephrased through the fact that there are some modes of the metric that become very strongly coupled as the temperature is lowered. So one cannot simply evaluate the partition function of the theory through semi-classical methods by just looking at the saddle point approximation. Now, luckily, it turns out that the path integral over this quantum mechanical theory can be performed exactly. And what one finds is the following answer, the logarithmic correction in S0 seemingly remained the same. However, now I get one loop correction that's dependent on the temperature of the black hole. And in addition to that, there's another factor that's less important, which is the semi-classical correction to the black hole entropy that is in the free energy linear in the temperature. So the important feature of this result, or the important observation, is that as we lower the temperature, this one loop determinant in the temperature can become very important in the computation. That's because this one loop determinant in the temperature can start competing with the logarithmic corrections in S0. So the point is that the new feature is that there are large quantum corrections at small temperatures that one couldn't see without doing this path integral over zero, this exact path integral over zero modes. And importantly, the important new feature is that the ratio between the partition function of the black hole when we take t to be exactly 0, and the ratio between the partition function of the black hole at a small but non-zero temperature actually goes to 0. And to be more precise, what we mean by goes to 0 is here one can actually argue that the entire loop expansion of all fields is regular in the temperature of the black hole. So when you take the ratio of the ratio between the partition function at 0 temperature and the non-zero non-zero temperature partition function, you can guarantee that this goes to 0. That this is very small, at least that it predicts at least a non-perturbably smaller degeneracy for extremal non-supersymmetric black holes than naively expected. So what I mean by that is that in principle, as the temperature becomes lower, specifically as the temperature might also be scaled with an exponential in the entropy, other non-perturbative corrections in gravity might become important, and we don't have any control over this. What we have control over is the entire perturbative expansion around the extremal black hole status. More precisely, this means that the degeneracy is exponentially suppressed compared to the expected result. So we expect that the degeneracy should go like an exponential of maybe some number times the entropy, with this number much smaller than 1. However, if we are to believe that some of the more recent results in toy models of quantum systems that are supposed to represent the physics of these extremal black holes, one might even conclude that the extremal degeneracy is 1. In any case, the point is that this correction that's logarithmic in temperature now addresses the second question that I posed, namely predicts that extremal black holes have a much smaller, extremal Reinstein-Nordstrom black holes in flat space, non-supersymmetric, have a much smaller degeneracy than naively expected. And in order to understand the result a little bit better, it is also useful to look at the density of states of the theory instead of looking at the partition function. So this we can look at by taking a simple Laplace transform of the result. So the result for near extremal black holes is the following. In the dotted red line represents the semi-classical answer, which is the result that doesn't take into account the regularization of these 0 modes at 0 temperature. So as you see in the, yes?
The semi-classical answer is independent of energy, right?
No, I mean the semi-classical answer.
The dashed line should be flat. I mean, I want to understand why it's going up as a function.
No. What I mean is that one can compute the semi-classical answer even for near extremal black holes.
And that gives you this upward trend.
And
that
this
is
gives you
true.
the support 10. Yeah,
Thank
so
you.
you can compute the action, right? The on-shell
Mhm.
action for any near extremal black hole. And it will
Right.
have some non-trivial temperature dependence. And then on
I
top
see.
of that, you could include the one loop correction from all these modes that had non-zero eigenvalue, but essentially like drop the contribution, the temperature dependent contribution of these zero modes. So this is what the dashed line represents. So while the purple line represents the quantum corrected answer, that also includes the zero modes. So, or would be zero modes. So starting on the right, we notice that at large energies above extremality, the answer predicted by ignoring these quantum corrections and taking them into account are very close to each other. That's because far away from extremality, the effect of these would-be zero modes are very small. That's because these modes actually at energy scales much above this scale, which is actually the gap scale, those modes become weakly coupled and can be treated semi-classically in this region. However, as I approach extremality and I reach this gap scale that I previously alluded to, you see that these modes cause there to be a very large difference in the predicted density of states. And importantly, all the way towards extremality, the density of states seemingly goes to zero. So the answer to question 1 and question 2 is that in Einstein-Maxwell theory, there is no gap. The role of the gap scale is that there's a set of strongly coupled modes that appears at that energy scale, and that there is no degeneracy at extremality, or at least that the degeneracy is non-perturbatively smaller than naively expected. Any questions?
So if there is no degeneracy, does that mean that the entropy goes to zero?
Yes. Which
So
is what you would
do you-
expect of a a conventional quantum system that doesn't have any symmetries that protects the degeneracy.
No, but I mean,
Maybe I can pipe in here. There's a question.
Yeah. Go.
There's a question of orders of limits. If you keep a quantum system size finite or a black hole finite and take energy to zero, the entropy does go to zero. On the other hand, if you take the temperature to zero, so you take the infinite volume limit first and then take the temperature to zero, then the entropy is still finite, even in this case. Yeah.
I completely agree. It's it's roughly speaking about the order of limits between S0 and T, right? Here, these quantum effects that became important occurred when the temperature was scaled like a polynomial in S0, right? When it was like m Planck divided by S0 to the free half. So to access black holes close to extremality, you actually want to study this regime in which the temperature and S0 could be scaled together with each other. And that's where the important physics of these modes comes from. This is how you have access, how you can see that the entropy close to extremality receives these very large corrections that push it towards zero.
I see.
So it's essentially because you are in a limit where you're scaling the temperature and the entropy of the system together.
Okay.
Does that answer your question?
Yeah.
Okay, great. Good. So how about black holes that preserve supersymmetry at extremality? The previous results seemed actually in tension with our basic expectations about supersymmetric black holes. Namely, we know from the state count of Strominger and Vafa that there are supersymmetric extremal black holes that have a non-trivial degeneracy at extremality. And we also know from the arguments of Susskind, Strominger, and Maldacena that I've referenced at the beginning of the talk, that those black holes are actually expected to have a gap. So if we are to trust the computation that I just presented, we should be able to redo the previous computation in the presence of supersymmetry and find these new features. So what changes in the computation of the partition function of black holes in supergravity? Well, there is still logarithmic corrections in the charge of the black hole that Sen and collaborators computed. There's still a semi-classical contribution that goes like the charge squared for, let's say, black holes in n=2 supergravity that have a single non-trivial charge. However, now I have to treat an integral over all these zero modes, but the space that parameterizes this zero modes is now slightly different. The space is a space of large super diffeomorphisms divided by super isometries instead of just being dFS1 times loop SU2. So actually, to describe the computation a little bit, it turns out that dFS1 times loop SU2 is a subgroup of the space of large diffeomorphisms. So it's the largest bosonic subgroup of this space. However, in addition to these degrees of freedom, there are large super transformations of the gravitino that, roughly speaking, couple transformations in dFS1 to transformations in loop SU2. And the space of super isometries is not only SL2R times SU2, instead it's a supergroup. It's PSU 1,1/2 for black holes and flat space, and SL2R times SU2 is the largest bosonic subgroup. So to answer what happens to these supersymmetric black holes, we have to perform this path integral. It turns out that for supersymmetric black holes, both in ADS and flat space, accounting for the would-be zero modes actually leads to a wildly different conclusion. Namely, while the integral over diffeomorphisms over isometries and the non-supersymmetric case gave a zero answer, it turns out that this integral over large super diffeomorphisms and the limit when the temperature is taken to be exactly zero gives 1 instead. So let's see a little bit how that comes about. So first, the contribution from the non-zero modes, as well as from the measure, the Q-dependent measure in these zero modes, gives the following factor when NH and NV are the number of hyper and vector multiplets in the theory. And in addition to that, the path integral at finite temperature over these would-be zero modes turns out to have an infinite number of saddles that are parametrized by this integer n. This infinite number of saddles come from the fact that we actually are fixing the angular velocity of the black hole by putting boundary conditions at the associated boundary conditions at the boundary of ADS2. And it turns out that when you fix the angular velocity, there's actually an infinite number of saddles that you have to account for. These are, roughly speaking, different saddles of the loop SU2 configuration and corresponds to black holes that have different angular velocities, but the same SU2 holonomy around the boundary of ADS2. So these saddles will actually play an important role. And evaluating the path integral over the effective theory of these would-be supersymmetric zero modes gives again one loop factor that turns out to be temperature dependent. It's also dependent on the number n that labels these saddle points. And the semi-classical answer, the semi-classical correction to the black hole entropy, again, turns out to be linear in T and also depend on n. Here, alpha is essentially a proxy for the angular velocity of the black hole, namely 2 pi alpha. I set 2 pi alpha to be omega times the inverse temperature of the black hole. So this is how the angular velocity of the black hole comes in. So this is the partition function for a black hole's a fixed charge, fixed temperature, and fixed angular velocity. Yes.
I have a question.
Yes.
Would one not have expected somehow naively that the original Schwarzian is sort of now replaced by its supersymmetric generalization? I mean,
yes. This is exactly where this result comes from. You take this theory of would-be zero modes that appeared even at quadratic order in the expansion of the gravitational action is now instead of that theory being the Schwarzian, it is now what's called the n equals 4 super Schwarzian. And the path integral in that theory can be computed exactly once again, and this is the exact result.
I see. Thank you. Thank you.
I have a naive question.
Yes.
Yeah. So when you're computing the gravitational path integral corresponding to the black hole, why do you zoom in on the near horizon region? Why shouldn't one take into account the entire black hole metric? I mean, the entire region which is covered by the black hole metric. I mean, of course, it would become singular at the origin, but I mean, there could be some cutoffs.
No, it wouldn't become singular at the origin. ADS 2 times S2 is just a subspace of the entire space-time, right?
No, it's a near horizon region. I mean, you're zooming in on the ADS2 cross S2 is just the near horizon region. The black hole metric encompasses a much larger region than that. I mean,
yes, I agree with that. Yes,
so
it's asymptotically flat. Yes.
Yeah, it's asymptotically flat. But why should one not consider the entire region covered by the black hole metric and just the near horizon region? That's my question.
Well, I guess first this is it depends where you believe that, roughly speaking, that this is a rough answer, but it depends where you believe the degrees of freedom that capture the entropy of the black hole lie. So for instance, if you consider the entire region, there will be fluctuations in all the fields that have no connection necessarily to the entropy of the black hole. So for instance, you could have arbitrarily large fluctuations for all the fields in the flat space part of the space-time, which also has an infinite volume. So to get rid of these problems, and we can think about a smaller region that includes the horizon of the black hole, and that's this ADS 2 times S2 region.
So you're essentially assuming the holographic conjecture. I mean, you're essentially assuming that the degrees of freedom of the black hole live on the horizon, on the near horizon.
No, not on the horizon, but perhaps I believe that in this case one can isolate the degrees of freedom of the black hole by looking at this near horizon region. I wouldn't say necessarily that the degrees of freedom are localized on the horizon or anything like that. I'm not sure that's meaningful.
Yeah, and so if you say that is not meaningful,
I have to say in higher dimensional ADS, one can actually do this computation in the full ADS space-time. the issue with the flat space computation and why we go to the near horizon region is because in flat space, we have an infinite volume in flat space where we don't have control over the fluctuations of all these fields at one loop order. But in purely ADS, asymptotically ADS space-time, so for instance, black holes, BTZ black hole, near extremal BTZ black holes, or black holes in ADS4 or ADS5, you could actually understand this by studying the entire space-time. Because there, we actually know that the states on the CFT count the black hole degrees of freedom that live in the bulk, right?
Yeah, but I mean,
and there you can actually consider the fluctuations of the fields on the entire space-time. And this has actually been done in the case of ADS-free black holes.
Okay, maybe we can talk in private.
Can I
Yes?
can I ask? Can I say something?
The
answer you gave to this previous question is a very reasonable one, that you are zooming on the horizon. But if you have an asymptotically flat space-time, we also know that black hole entropy is evaluated by the Gibbons-Hawking term, which sits as infinity. Is there some tension between these two statements?
No, because here we've also evaluated the black hole entropy using the same Gibbons-Hawking term that is now, roughly speaking, moved at the boundary of ADS2 times S2. So the way in which you can view this computation is you put some boundary conditions at infinity. The boundary conditions that Gibbons and Hawking studied for black holes in flat space, namely that the time circle is periodic with period beta, and you put Dirichlet boundary conditions on the metric and let's say on all your gauge fields, and then you study, given those boundary conditions at infinity, what boundary conditions do you have to put at the edge of the throat of this black hole that are consistent with the boundary conditions at infinity. So if you impose those boundary conditions, it turns out that you have to account for a Gibbons-Hawking York term at the edge of the throat as well. And what that Gibbons-Hawking York term captures is the action, roughly speaking, the contribution to the action of the Gibbons-Hawking York term at infinity, plus the evaluating the action in between infinity and the edge of the throat. So essentially, like I would say that one can evaluate the free energy of these black holes semi-classically by just looking at the near horizon region entirely. Because if you impose the correct boundary conditions at the edge of ADS2 times S2, you find that you also have to add a Gibbons-Hawking York term to your action that lives at the edge of ADS2 times S2.
Yes, I understand. Thank you.
Okay. Okay, so great. This is the partition function for fixed angular velocity. And now we can again Laplace transform this answer, this entire answer, both with respect to the temperature and with respect to the angular velocity omega, to now look at sectors of fixed angular momentum. So this is how the density of states looks like in the sector of angular momentum with J equals 0. So once again, the semi-classical result that Subir asked about previously looks pretty much unchanged. That's because once again, the free energy of these black holes has some non-trivial dependence with the temperature, and the one loop corrections around these backgrounds doesn't actually contain any temperature dependent piece if you ignore the presence of the temperature dependence induced by these would-be zero modes. So again, starting far away from extremality, the semi-classical answer and the exact answer, including the quantum corrections that's shown in purple, are very close to each other. However, as I approach extremality, I see a completely different behavior from the non-supersymmetric black holes that that we studied earlier. Namely, at the gap scale, what happens is that the density of states vanishes exactly. This can be observed by, it's a bit hard to observe, but it turns out that while each of these terms in the sum over saddles turns out to have a smooth Laplace transform, the Laplace transform of this function is a Bessel function, the sum over all these Bessel functions contains an exact gap in this region. So below this energy scale, there's a gap. And the sum over all these Bessel functions also gives an exact delta function at extremality, whose degeneracy is proportional to S naught to some power times e to the S naught, where this power precisely agrees with the prediction of Sen and collaborators that in turn matched the answer that Strominger and Vafa and many other entropy counts obtained. So this answers question 1 and question 2 in the case with supersymmetry. For black holes, for supersymmetric black holes in flat space, there is actually a gap and there is a massive degeneracy. And this is all consistent with the expectations from microstate counting and with stringy constructions of the gap. Now, I want to mention also that one can compute this density of states in sectors of angular momentum that are not zero. And it turns out that, for instance, for angular momentum 1, the density of states, for angular momentum half, the density of states starts precisely at this gap scale and has a slightly different behavior at higher energies. For angular momentum 1, it also starts here. And if I go to higher and higher angular momentum, it turns out that the density of states starts at E gap multiplied by different integers that depend exactly on the angular momentum sector that I'm studying. The reason why I mentioned this is that this result shows that this degeneracy, this delta function that you can see in this plot, is only a feature of the j equals 0 state. Which means that all the black holes all the supersymmetric black holes that are under study here are not only purely bosonic, but they also don't carry any angular momentum. And this is the reason why the index of these black holes is actually the same as the degeneracy of these black holes. And the similar argument was given by Sen and collaborators, though I think this argument is a slight refinement because it includes the contribution of these regularized zero modes. Okay. So to summarize, both in the non-supersymmetric and supersymmetric cases, we have found a set of modes that have zero action at zero temperature, which means that they are very strongly coupled. And the major difference between the non-supersymmetric black holes and the supersymmetric ones was that this integral in the non-supersymmetric case gets regularized to 0 when the temperature is 0. While in the supersymmetric case, this integral gets regularized to 1 when the temperature goes to 0.
I have a question here.
Yes, please go ahead.
I mean, as Subir was saying, since when the temperature goes to 0, the entropy automatically goes to 0. That corresponds to the previous case. But why shouldn't it hold here also? I mean, when temperature goes to 0, that the entropy of
it's not true that in any quantum system the temperature goes to 0. The entropy goes to 0 and the temperature goes to 0. That's only in systems that don't have a degeneracy that's protected by some symmetry principle usually. In this case, supersymmetry, due to supersymmetry, the index of these black holes is protected as we vary, let's say, the string coupling, and one actually can compute the index at weak coupling and find a very large degeneracy, which needs to also be there at strong coupling. So this tells us that there's a symmetry principle that protects this degeneracy, and this is why the entropy of these black holes is non-zero.
I see.
So essentially, supersymmetry protects this degeneracy.
Okay.
Okay. Are there any questions? Perhaps I can go really quickly if there are 10 more minutes and there's interest. I could go also through the localization computation for the degeneracy and extremality. Otherwise, I could also stop here because I know it's been an hour.
Oh, sure. You can take 10 minutes. It's okay.
Okay. So far, we've found a very encouraging signal for a conventional quantum mechanical system. Even using the gravitational path integral, we found an exact degeneracy at extremality, which is gapped out from the rest of the states. And this is a pretty strong signature that there is a genuine Hilbert space that the gravitational path integral can see that's associated to these BPS black holes. However, so far, the computation has shown that the degeneracy is given by, at one loop order, is given by this answer, S naught to some power times e to the S naught. S naught depends on the charge of the black hole. However, this answer for the degeneracy is not always an integer. Namely, I can always plug in, even if I correct this by an order 1 factor, I can always plug in different charges for the black hole that I'm interested in, and all these results won't be on integers at once for all charges at the same time. Of course, perhaps that's expected, because so far I've only included all loop corrections in the zero modes. This is how you get this exact delta function, but only one loop correction for all the other modes. And you shouldn't be able to see the exact degeneracy by only looking at one loop corrections for some of the modes. So can we do better for extremal supersymmetric black holes and reproduce the degeneracy in a microscopic model? And the model that I'll be talking about are 1/8 BPS black holes in n=8 supergravity and 4D flat space. And the entropy or the degeneracy of these black holes is known from a state count in string theory by Maldacena, Moore, and Strominger. So the charges of the black holes actually are captured by the Fourier coefficients of a weak modular form with weight -2 and index 1. That depends on two integers, n and l, that correspond to the charges of the black hole. And it turns out that the index of this black hole, so this Fourier coefficients computes is believed to compute the index of the black hole. The index does not depend on n and l independently. It only depends through this factor of delta, which is what's called the U-duality invariant. That can be defined for black holes with arbitrary charges that come from the compactification of 10D supergravity on P6. Here, P are magnetic charges and Q are the electric charges. Good. So the beautiful thing about this microscopic degeneracy that people obtain from string theory is that it admits a Hardy-Ramanujan-Rademacher expansion in which the index of the black hole can be written as an infinite sum of analytic functions. So to unpack this formula, this sum contains a sum over Bessel functions, in which Bessel functions grow exponentially, but they become successively smaller as C grows. And it also contains a Kloosterman sum, which in turn is a sum over exponential phases. That won't be that important in this talk. The only important feature is that it doesn't grow with delta. So let's interpret this formula a little bit. This is just a mathematical formula that's related to modular forms, to the fact that we're expanding the Fourier coefficients of a modular form. But let's unpack and try to find the physics from this formula. So let's expand this formula at large delta, which corresponds to large black hole charges. So the leading answer comes from the C=1 term in this sum, and is given by e to the pi square root of delta. Now, the nice thing is that pi square root of delta was previously identified exactly with the area over 4G Newton for the black holes, the supergravity solutions that were believed to be the ones for which this calculation counts their entropy. So this is good because it shows that the leading answer in delta seems to agree with the semi-classical predictions for the corresponding black holes in supergravity. Now, at subleading orders, non-perturbative orders, if I look at the leading contribution of a saddle with of a term with C different than 1, then one finds that the Bessel functions grow like e to the pi square root of delta divided by C, as long as C is much smaller than square root of delta. This is the case. And this term can be identified with area over 4C G Newton. And this actually was previously identified with the free energy, not of the original black hole solutions, but of orbifolded black hole solutions that satisfy the exact same set of boundary conditions as the black holes that had this area. And finally, when C is very large, when C is much larger than square root of delta, this Bessel function no longer has an exponential growth, but instead it decays polynomially with C due to this factor of C to the -9/2, which essentially guarantees that the sum eventually becomes convergent at very large C. So given that we've kind of interpreted this formula that came from string theory through a semi-classical prism, one might wonder whether we can reproduce this formula exactly by using the gravitational path integral. And a lot of progress has been made in this direction using the technique of localization in supergravity by these author and several more. The computation was always, the computation of this degeneracy was always very close, but there were several ingredients that were missing, and we can still discuss if there's, there will still be a few steps to do even in our computation, but I think we're closer to the final result for this degeneracy. Good. Here, our starting point is we want to compare apples to apples. So we want to compare the index in string theory to an index obtained from the gravitational path integral. So first of all, the first question is, how do we compute an index at the level of the gravitational path integral? Well, an index has a -1 to the f insertion, and this -1 to the f can be interpreted as turning on a non-trivial chemical potential for the angular momentum of the system, such that I insert e to the 2 pi ij in the path integral. That's one way of always rewriting -1 to the f, but inserting e to the 2 pi ij is equivalent to setting the angular velocity times theta to be equal to 2 pi, angular velocity in Euclidean signature. So essentially, the boundary conditions that we have to impose at the boundary of ADS2 times S2 space-time is that we have to turn on a non-trivial angular velocity for the sphere. And this is what will compute the index of the theory. Then at the same time, to go to this near extremal limit, I will take beta to be very large as I keep this fixed. For these types of space-times with these boundary conditions, it turns out that asymptotically there is a PSU 1,1/2 isometry. It's the same isometry that I talked about earlier, but this survives even when I turn this angular velocity. And one can consider a killing spinner of PSU 1,1/2, such as that it squares to this combination of killing vectors where L0 generates these rotations in ADS2 and J0 generates these rotations on S2. And as people have done previously for computations in supersymmetric quantum field theories, one can find the localizing term using this supercharge or killing spinner, which leaves the partition function invariant under the coefficient, under changes of the coefficient lambda of the localizing term. So one can, if the partition function is independent of lambda, one might as well evaluate the partition function when lambda is equal to infinity. And in that case, and that will be the same as the partition function of the undeformed theory. But the advantage of evaluating when lambda is equal to infinity is that we can simply evaluate the partition function by looking at the saddle points of the deformation terms and by evaluating the one loop determinant around these saddle points. So the path integral turns out to localize to the places where the killing spinner acting on all physical fermions in the theory has to give 0. And there are two implications of this set of equations. First, if we look at the equations where the physical fermions are part of the graviton multiplet, then it turns out that there are two. Then it turns out that the space-time has to look like ADS2 times S2 locally on the entire geometry. However, globally, there's two possible forms that this space-time can take. It will either look like ADS2 times S2 or like an orbifold of ADS2 times S2. These turn out to be the only two geometries that satisfy the boundary conditions that I mentioned that actually preserve the presence of this killing spinner with respect to which I do the localization computation. And while a priori this is unclear, here we will take the perspective that the gravitational path integral requires a sum over all geometries that are consistent with the boundary conditions that I impose, regardless of the topology of the space-time. So here I'll take the perspective that one should sum over the contributions of ADS2 times S2 and the contributions of these orbifolds. Now, if I look at what the localization computation tells me for the physical fermions in vector acting on the vector multiplets, it turns out that the localization locus gives that there's an entire localization locus for all the scalars in the vector multiplets. And we will parameterize the localization locus by a set of real numbers phi I, with one real number for each scalar in a vector multiplet, with I going from 0 to NV. So now, in order to evaluate the gravitational path integral, one has to just integrate over the localization locus and compute the one loop determinant at each point on the localization locus. So first, supergravity action can be evaluated at each point on the localization locus exactly, and is only dependent on the prepotential of the theory. In n=8 supergravity, the prepotential is exactly known. And a similar computation can be done on the orbifold geometries. And the answer is very similar. The only difference is that the on-shell localizing action is suppressed by a factor of 1/c, because roughly speaking, the volume of this space-time is smaller by a factor of 1/c. And the one-loop determinant on this different space-time can now have a non-trivial C dependence that I have to be very careful about. And in addition to that, when evaluating the action on these geometries, it turns out that there are topological terms which yield the Kloosterman sum, which appeared in the Rademacher expansion that I mentioned previously. So I won't have time to talk about this, but it's there on these orbifold geometries. In n=8 supergravity, the prepotential turns out to be quadratic in all the scalars except for the phi naught, which is the scalar in the graviphoton multiplet. So I can integrate out phi1 through phi and v, and one gets the following answer for the path integral over these black holes, where the missing ingredient is this one loop factor, which turns out to only depend on phi naught, which roughly speaking sets the size of the ADS 2 times S2 region. So a lot of progress had been made in computing the one loop determinant as a function of phi naught for all supermultiplets, but the contribution from all supermultiplets had not been computed. So once again, we can look at the one loop expansion of the QV term, and notice that again, there are modes under which that are zero modes of QV. And these are the same zero modes that were zero modes of the supergravity action. So once again, we can try to separate the contribution of these modes into a contribution of non-zero modes and a contribution of zero modes. So first, let's discuss the contribution of non-zero modes. So it turns out that for the boundary conditions that we impose, perhaps I should mention this in a bit more detail, since Sok had a recent paper about this. But at the boundary of ADS 2 times S2, we are not imposing Dirichlet boundary conditions for all the fields. Instead, we are imposing boundary conditions that come from imposing Dirichlet boundary conditions all the way out at asymptotic infinity, and looking what boundary conditions one has to impose at the edge of the Froh. And it turns out that with those boundary conditions, it's indeed consistent. One has to integrate over all modes for which bosonic and fermionic modes are paired with each other. Because one can pair all bosonic and fermionic modes, it turns out that the one loop determinant for all of these supermultiplets can be computed using a fixed point formula, as long as one chooses the boundary conditions that I mentioned. And the result is a complicated expression that depends for each supermultiplet, each n=2 supermultiplet that is part of the n=8 graviton multiplet. It turns out it's a complicated expression that depends on the size of ADS 2 times S2, which here is parametrized by phi naught, and on the orbifold parameter C. And here's the answer that we have for each n=2 supermultiplet that we can put together to form an n=8 graviton multiplet. Now, when we put things together to form an n=8 graviton multiplet, it turns out that the answer has very simple phi naught dependence, and is completely C independent. So it gives this power of phi naught to the fifth. And similarly, just as before, we can compute the contribution of the zero modes, which are zero modes of QV, by doing an integral over large superdifeomorphisms divided by superisometries on both the ADS 2 times S2 geometry and on this orbifold geometry. And the answer is this factor of 1 over C times phi naught. So the only C dependence, at least as far as we can see, comes from this integral over superdifeomorphisms that exist both on the orbifold and on the regular geometry. So now we can put everything together and we simply get a single integral over phi naught that remains, where this factor comes from the non-zero modes, and this factor comes from evaluating the path integral over zero modes at each point on the localization locus. And massaging this expression a little bit, one finds precisely the Bessel function that I was talking about earlier. And importantly, in order to get this factor of C to the -9/2, here I had to do some rescalings of phi naught in order to get that factor. But importantly, I needed precisely a factor of 1 over C from the one loop determinant, either of the zero modes or the non-zero modes. But in this case, it came from the one loop determinants of zero modes. So accounting for that one loop determinant was critical in order to get the right power of C that is the power of C that one encounters in the Rademacher expansion. So to see how this formula works in practice, let's look at a black hole whose U-duality invariant combination of charges is equal to 200. So this was 4n minus L squared, and one can choose n and L such that you get 200. So the leading saddle is simply given by the Bessel function with C equals 1. And this gives this very ugly number. As I include the next saddle, you observe that the contribution of the next saddle is immediately much smaller. That's because it's reduced by a factor of 1 over C that is included in this Bessel function, and the Bessel function decreases exponentially due to these factors of 1 over C. And I can keep including more and more subleading saddles, which correspond to orbifolds that are sharper and sharper. And one notices that the sum converges very quickly. And even including the first 5 saddles, one gets this answer, which should be compared with the exact string theory answer for delta equals 200, which is this. It turns out that including all saddles, you get better and better convergence, and eventually you get the exact string theory result. Perhaps I should mention that if you know that the result that you're going to get is an integer to begin with, you only need a very small number of saddles to arrive at the correct integer. You can take the integer part of this, and of course you get the exact result. But we don't have to assume that the sum is sufficiently convergent to give the exact integer. So the answer from all this is that the black hole partition function, when we account for the localization for the one loop determinant in the localization computation as we did, and we can discuss what assumptions went into that, is that the black hole, the computation from the gravitational path integral that computes an index agrees with the black hole index obtained from string theory, and thus we can seemingly obtain an exact integer from the gravitational path integral. So to conclude, I just want to give some concluding remarks about ADS2 holography more broadly. So in higher dimensional holography, the scale of quantum gravity corrections is controlled by the ratio between ADS and L Planck. This is what we typically call N. However, in ADS2 holography, there are 2 scales that we should be concerned about. The first one is S naught, the entropy of the black hole, which goes still, we should interpret as related to N. This is given by the ratio between the ADS size and the Planck scale, or in the case of black holes in flat space, the size of the S2 and the Planck length. But in addition to that, there is another scale, which is the ratio between the temperature and the gap energy scale. And while in higher dimensional ADS, of course, I can also introduce a temperature. If I go in the regime of small temperatures, I'm close to the higher dimensional ADS vacuum, above which all excitations are gapped by order 1 factors. One can compute the spectrum of those excitations semi-classically, given the Lagrangian of the gravitational theory that I'm talking about. They're just the fields in the effective action. However, in ADS2 holography, in the limit in which the temperature is very small, the spectrum is controlled by the presence of the zero modes that we showed, that we saw in this talk, which turn out to give a non-perturbatively dense spectrum even at low energies. So as opposed to the higher dimensional ADS case, in ADS2, the energy spectrum above t equals 0 always contains a very very dense set of states. And nevertheless, this density of states, it was controlled by the one loop determinant of these would-be zero modes when I turn on a temperature. There's little hope, I think, of getting the exact energy levels in this continuum density of states. However, in the supersymmetric case, we actually separated a discrete set of microstates, which were those associated to BPS black holes. And moreover, to account for the exact degeneracy of these BPS black holes, the sum over topologies was both necessary, but luckily it was also under control. And that's what allowed us to actually predict compare the degeneracy of these BPS black holes to the ones from string theory. And I think that this is worth pursuing even in other examples with less supersymmetry. Here we studied black holes in n equal 8 supergravity, but one might even go to n equal 4 or n equal 2 supergravity, because it offers an example of exact ADS2 holography, where we have control over discrete part of the Hilbert space with the gravitational path integral alone. Okay, thank you very much.
Thanks, Luca, for a nice talk. Are there any questions?
Yes, I have a question. Let's look at the non-supersymmetric calculation that you were doing.
Yeah.
And
sorry, perhaps allow me to rotate, because in the meantime, the sun has risen and I can't see anything. Yeah. Okay. Sorry. Go ahead.
Yeah. So so this spectrum. Let's look at the left-hand side figure in the non-supersymmetric case, where you have a gapless spectrum, and this essentially came out of looking at the very low-lying modes, low temperatures of the near extremal black hole. Now, this spectrum is also the spectrum of the SYK model, right?
Yes. Well, the coarse, I would say that the coarse-grained spectra are the same. And SYK, I can also actually put SYK on a computer and get the exact set of energy levels given some coupling.
Yes.
But they only agreed at a coarse grain level.
Yes, okay.
spectrum
I
of
understand.
SYK with the
Understand. So
spectrum.
my question is the following, actually, that the SYK model is a model of microstates. No, there are microscopic degrees of freedom.
Yes.
Can I sort of extrapolate and declare that those degrees of freedom are the microstates of the four-dimensional black hole also, from where this was descended?
In my opinion, the best one to do, perhaps Subir could also say something about this, but in my opinion, the best thing that one can do is show that there's an agreement between the coarse-grained spectrum of SYK and that of 4D black holes. I don't think one can use SYK or any other model to predict the exact spectrum of these 4D black holes. Because in SYK, I don't know the exact set of couplings that I have to choose in order for which member of the ensemble I have to choose in order to really study a specific black hole in a gravitational theory. But I think they agree at a coarse-grained spectrum, and that's because the low energy theory that captures both the density of states in the black hole and the density of states, low energy density of states in SYK is the same theory. It's the Schwarzian theory. But I don't know if beyond that one can capture one can capture the exact spectrum of the black hole. Perhaps I can say that I believe that one can capture something slightly more than just the density of states itself. Namely, we can view rho of V as, since it's a coarse-grained density of states, as an average over the exact density of states over some energy window. Perhaps SYK is also good at capturing higher moments of the averages of our densities of states. So perhaps SYK correctly predicts what the correlator between rho of E1 and rho of E2 is. This can be compared with wormhole computations in the gravitational path integral. But I don't think one can capture the exact spectrum.
Maybe I can add a comment. So I think I agree with everything Luca said. Now, even for the density of states, there's a exponential factor and then the square root of energy factor. But then there's a prefactor, which in this case is a power of the area, whereas in SYK, it's just a power of n. And that prefactor really depends on the actual spectrum of the theory. And in fact, even for SYK, the power of n that you get depends on whether you're talking about SYK4 or SYK6. It really requires the microscopics, which you just cannot get from the ADS2 path integral. Yeah, so there's an overall power law prefactor, which is also different.
Okay, thank you.
Any other questions?
Yeah, I have a question. Why is the string computation matching so perfectly with the supergravity computation? That isn't that somewhat intriguing? I mean, because
I think it's because both quantities are in some sense protected. The index in string theory is protected. It's actually computed at weak string coupling and extrapolated in this gravitational regime, because we know that the index is independent of the coupling. And in the supergravity computation, one thing that's intriguing, and perhaps it's related to what I just said, is that when evaluating higher derivative corrections that come from string theory and that are present in the supergravity action, those corrections vanish when you evaluate them on the localization locus. So that indicates again that the answer in the answer that one obtains from the gravitational path integral is in some sense universal because it's independent of the string coupling as well.
I see. And in that case, why doesn't the, I mean, so you said that the supergravity and the string theory computations are protected because of the supersymmetry, but then that won't apply for the case of the previous, I mean, the non-supersymmetric black hole, right?
Yes, of course, yes.
Yeah. So in that case, isn't that a possibility that the string theory computation would give a different result than the gravity computation? Isn't that possible?
Well, I don't think there is a string theory computation. Well, okay. There are string theory computations that try to predict the degeneracy of non-supersymmetric black holes. I'm not sure about the validity of those computations because they rely on a weak couple. They typically rely on a weak coupling answer matching a strong coupling answer without necessarily having the guarantee that they match. Yeah, protection due to the supersymmetry. Yeah, yes. Without having the same property as the index, right? Which we know we have a proof that it's protected by supersymmetry.
Yeah, but
even there could be phenomena such as wall crossing and things like that in which the index can jump. But okay, neglecting those or how should I say? Let's say being careful about those effects that in this case don't occur in any equalized for gravity. One can see this match.
Yeah. Okay.
Yeah. Thanks, Luca, for nice talk. I just want to had a technical question. So in calculating the determinants, you somehow use normalizable boundary condition on the full space time. Is that the point?
Yes. You use normalizable boundary conditions on the asymptotic.
I see. So,
as you know very well, normalizable modes as you pointed out in ADS 2 times S2 are not paired only with normalizable modes by supersymmetry in ADS 2 times S2. But if you look in asymptotically flat space, normalizable modes in asymptotically flat space are only paired with normalizable modes in asymptotic flat space through supersymmetry. That's because the killing spinner doesn't grow at infinity in flat space. So what we do is the philosophy that we always try to follow is we impose boundary conditions all the way out at infinity and deduce the boundary conditions from the boundary conditions at infinity, deduce what boundary conditions we have to impose at the edge of the throat. And that also dictates what modes the boundary conditions also dictate what modes you have to integrate over, right? What fluctuations you have to integrate over. And since normalizable modes in flat space always pair with normalizable modes in flat space, and we have to integrate over all those given Dirichlet boundary conditions in the asymptotically flat regions, that indicates that we have to integrate over all those modes. And that comes about by deducing the boundary conditions that the Dirichlet boundary conditions in the asymptotic flat space region imply for the edge of the throat. So I think the confusion that we were having previously, the confusion, maybe the thing that we didn't communicate to you well enough is that we're not imposing Dirichlet boundary conditions at the edge of the throat. We're just deducing what boundary conditions we need by looking at the asymptotically flat region.
So doesn't that mean that you are doing localization on the full space-time rather than on the near horizon geometry? Because these determinants are really the determinants of the modes in the full space-time, right?
Yes. Roughly speaking, yes. I think I agree with that.
I see. So
but
localization in full space-time, right?
Yes, I would say that. Although perhaps the only caveat is that we didn't use we didn't use the full geometry in the localization computation, but perhaps that's a detail. As in, when we looked at the action on the localization locus, we didn't actually write down the geometry on the entire space-time and evaluated the action on the localization locus for the entire space-time. We evaluated the action on the localization locus for this near horizon region. So including the boundary conditions that come from, imposing Dirichlet boundary conditions in the asymptotic part of the space-time. But perhaps what would be nice would be to indeed do the computation where one finds the localization locus for the full geometry that goes to asymptotic flat space, and do the computation entirely there without ever referring to this ADS 2 times S2 region.
I see. And now,
sorry, go ahead. The only thing sorry, you go ahead.
Go ahead. No, you go ahead, please. Yeah.
Okay. The only thing I was going to say is that perhaps one nice thing of doing the computation in the full space-time is that the index should not depend on the temperature. Even though you impose that the asymptotic time circle is periodic, the fact that you impose an angular velocity, turn on an angular velocity that computes an index, should explain that, should show you that the index does not depend on temperature. So the localizing configurations that you get when you, for instance, study large temperatures should not even include an ADS 2 times S2 portion of the space-time. Now, of course, if you just study the t going to 0 limit, that includes those geometries will most likely include this ADS 2 times S2 factor. But the point is, if you do the localization computation in asymptotic flat space, I think you might even get away with geometries that don't even resemble these extremal geometries at all.
Yeah. Okay. So what I was asking is, now suppose you embed the same near horizon geometry in a different asymptotic space-time, say ADS4 or something else. The determinants change, or will they remain the same?
You mean you keep the exact
same near horizon geometry, but the asymptotic geometry suppose is different?
Yes, but do you keep the supergravity theory to be the same? That probably also changes.
Supergravity theory is the same.
But don't we have to talk about gauged versus ungauged supergravity if we go from asymptotically ADS to from asymptotically flat to asymptotically ADS?
See, the example that I can think of, maybe not ADS, but using this 4D, 5D lift, the same near horizon geometry you can regard either as part of a 4D black hole or as part of a 5D black hole.
Yes,
right?
yes,
And
yes. Those are both asymptotically flat, right?
Yeah, those are both asymptotically flat, but the asymptotic geometry certainly is very different.
Yes.
And normalizable modes in one geometry may not mean normalizable modes in the other geometry.
Yes.
But the determinants will remain the same.
I'm not sure. So this Atiyah-Bott fixed point formula that we've used has the following requirements. One is that all the modes are paired. And the second is that the computation relies on the action of the killing vector, that's the killing spinner squared, at the fixed points of this killing vector. You essentially have to find what the representation of all the fields that you're integrating out are under the action of this killing vector, and see what happens at the fixed point of the geometry. So as long as the fixed point is the fixed points are the same in both geometries, and as long as the action of the corresponding killing vector is the same at that fixed point, the one loop determinant will be the same. I don't know if that's the case in the two examples that you mentioned, but that's what I would check.
I see. Yeah, meaning what I find surprising is that at least in calculating the logarithmic corrections, we really impose the normalizable boundary condition at infinity, right?
Yes.
At the edge of
Sorry, the normalizable boundary. The normalizable boundary conditions at the edge of ADS 2 times S2. You mean?
That's right. Yeah, yeah.
Yeah, I find it very interesting that this calculation, which seems to be a calculation in which, as I said, you take all normalizable modes in flat space, and those include some modes that are non-normalizable in ADS 2 times S2, agrees with the calculation of purely normalizable modes in ADS 2 times S2 at one loop order. That I cannot explain.
Okay.
But perhaps supersymmetry is the reason why they agree. I'm not exactly sure.
Okay. Yeah. Okay. Thank you very much.
Of course. Any other questions?
Yeah. I guess there are no more questions. So yeah, thanks, Luca, for the very nice talk.
Thank you.
Yeah, thank you
Thank
very
you.
much for the invitation. If there are any more questions, please feel free to send me an email
Sure.
or anything.
Thank you.
Thanks very much. Luca.
Okay.
See you next
Yeah.
time.
Thank you. Yeah.
Thank you.
Have a good day or
Bye.
a good evening.
Good day.
Yeah. Bye.
Bye.